Good morning, everyone. So on behalf of the Fields Institute, my name is Ian Hamilton, the director here. We've been so delighted to have this seminar in machine learning. This is almost the end of the academic year's program, but I thought it would be timely just to come in and say how pleased we are with the whole project, and also to congratulate Tommy, Jordan, Richard, Professor Hinton on the launch of the Vector Institute, which is, of course, a fantastic development. And in some way, perhaps this was kind of a lead-up, I don't know. But I won't take up any more of your time. Just welcome to the Fields Institute and enjoy your lecture today. Thanks.
It'd be good if everybody thanked the Fields Institute, actually. I think it's been a great place to have this. And we're looking forward, we're trying to do the same thing again next year. So we should thank the Fields. Okay, so today I'm going to introduce Max Welling, our speaker. Max did his PhD in physics, and he has a background in physics, but then he's gone on to do amazing work in machine learning. He did postdocs after PhD, both at Caltech, and he was here in Toronto, one of our illustrious alumni here in 2001 to 2003, so quite a while ago. And he was telling me this morning as he walks around, many things are just the way it was in 2001, 2003. He's now a research chair in machine learning at the University of Amsterdam, and he's been a program chair at NIPS, at AI Stats, ECCV. He's got all kinds of awards, best paper awards at ICML, Kundering Prize at ECCV. So he's done really gotten recognized for all the work that he's done. To me, of all the people in the field, he really is the prime example of kind of why we're started this whole series here at the Fields. He's an exemplar of somebody doing amazing work in research, but also doing work with companies and applications. His research has been very significant in all kinds of areas. A lot of work on probabilistic models, on sampling, on scaling up networks and doing things in a distributed way. Lots of work on deep learning. And recently, a lot of applications in things like medical imaging, and started a lab doing that. And he also has his own startup company called Cypher, that works with all kinds of companies, and it's a deep learning spin-off. So in that way, that's why I said he kind of combines the whole idea of doing great research with actually working on applications. He's also become a bit of a celebrity in Europe. So I was visited him recently there, and he's written some newspaper articles on AI and big data, and one of them even had a little comic that Max was in. So he's become a bit of a celebrity. So it's my pleasure to introduce Max. One thing before we start is I wanted to say that this is the first of our talks in this series that's going to be live cast in Waterloo. And there's people on the line now in Waterloo as part of Communitech. Around how many people did you say? 40 people are watching this live cast. So it's an exciting development. So the other aim of this whole series was to reach out not only in Toronto, but also in other parts of Ontario, especially like Waterloo and the other universities. And so this is our first step along the way. All right. So great. So take it away, Max.
So thank you very much, Rich, for the. I was going to say if you're able to speak well, how do you want me to talk like this? Oh, hello. I hope I could just speak like this. It's fine. So thank you very much, Rich, for hosting me here. I'm going to be here for a week. It's super exciting for me to be back here. I have many old memories navigating the corridors here, and so it's very interesting to me. Also, I want to say in Europe, I'm not all that much of a celebrity. It's much like in the land of the blind, the one-eyed is king. And actually, I'm very impressed by everything that's happening in Canada. The things here are definitely on a different scale than the thing that we do in Europe. And I hope that in Europe we can sort of start to match whatever you're doing here. And so Canada, for me, in many ways, is a big example, and I think, you know, you should be very proud of what's happening here. It's really great. So I wanted to also say there is two things that which didn't mention, which is one is two labs. One is the Qualcomm lab, which is 10 PhD students, and this is a Bosch lab, Delta lab, that we opened very recently, again with 10 PhD students and postdocs, all doing research in deep learning related areas. So this is what the Netherlands looks like today. It happens to be King's Day, and it's really fantastic. Everybody's going out. This is Amsterdam, people on the canal with boats. Everybody's dressed up orange. So if you want to visit Amsterdam one day, today is a really good day to be there. So I'm going to talk about three sort of ways that we try to improve deep learning, in particular convolutions. One is generalizing convolutions to larger symmetry groups, and the second one is generalizing convolutions to graphs, and then the third one is sparsifying and compressing neural networks and also convolutional neural networks. So first a little bit, so this for many of you might be sort of a little bit oversimplified, I don't know. So how many people are very familiar with convolutional neural networks? Is this everybody basically in the room? Are there people who are, yeah, most people are, I guess. So a convolutional neural network is basically, you start out with a signal, high sort of sampled, height rate sampled signal, like an image or a speech signal, and you have a little sort of template which you run over the image, and that's sort of, the operation is called a convolution. And you sort of filter the image into different sort of filtered images here. So you have different filters you run over the image, and you get different sort of filtered images out. And then you repeat that. So you do a downsampling of that, typically, and then after the downsampling, you have another set of filters that you run on each one of these. And so you get more and more smaller and smaller filter maps. And then in the very end, you basically have a very large set of very small filter maps that you then process through a normal sort of fully connected neural net to give you an output, which is sort of a prediction maybe of a particular class. And the beauty is that you get sort of this hierarchical sort of representation where the first layers, they do very simple things like detect edges, and the deeper you go, sort of these hidden units, they start to represent more and more abstract things. Like this is trained on faces, so you get neurons which start to focus on eyes or eyebrows or ears or noses. And then at the very end, you get things which sort of have the receptive field of an entire face, and they start to sort of model sort of different types of faces. And this is sort of a convolution. This is one of these things that runs over the image and takes the inner product with the image. Now, I start, talking about my own work. I just wanted to give you a little bit of background on what has been happening recently in this field, and it's just this year. So this is just 2017, and I'm just going to show you three results of three groups where people used convolutional neural networks to really improve state of the art in medical imaging. And in medical imaging, I'm starting a sort of small group in medical imaging as well. And it's really amazing what has been happening just in 2017, where we now see three totally different application areas where deep learning has beaten physicians in doing certain types of diagnosis. So this is the first paper. It's a Nature. It appeared very recently, a couple of months ago, where the authors collected 130,000 images of skin lesions, and they wanted to classify those in 757 different classes. Like one of them could just be a mole, another one could be melanoma, which is a very terrible sort of cancer, skin cancer. And so the results were plotted like this. So here you have specificity, sensitivity plotted out. Every dot is a dermatologist, between 20 and 25 dermatologists. and the blue curve is the computer, basically the algorithm run at different operating points. Humans only operate at one operating point, so there's one red dot. And what you see is basically that if you're below this blue dot, then the computer is better than the human. And these were tested quite rigorously, so you know, I believe these results. And what you see is that for certain things like detecting melanoma or carcinoma, you see that there's very few dermatologists which actually perform better than the algorithm, and in particular, the average performance is way below the algorithm. And so this is the second one. This was in the Dutch news. You know, this is Dutch, of course, but it's basically saying that the computer can recognize cancer better than a pathologist. So here the case is you take a piece of tissue from a tumor, and you need to identify those regions where, let's say, cell division is faster or different than what you would have for normal cell division, and you would want to predict where the tumor is and what grade it is typically. So this is only where the tumor is. These are very large slides, you know, gigabyte per slide or something, and it's very tedious work for a pathologist to look at these things, and there's many that they have to study. You know, they get tired, you know, they miss things. And they took a neural net. Google did this in collaboration with a Dutch group in Nijmegen. Now they quote numbers here where 89% the algorithm was correct and the pathologist 73% correct. And here's a third one, which is retinopathy. Also, it's all 2017, by the way. It's really recent stuff, where you take an image of your retina, and then again you look for lesions or irregularities in the retina, and you find certain places where this is happening, and then you can predict whether this person has diabetes 2, I think, disease, and is in danger of sort of, you know, becoming blind. Again, here they did the similar kind of graphs. In this case, you know, the dots are the doctors again, and the lines is the algorithm. So I think here actually ground truth comes from humans, so it's very hard to beat humans because the labels are directly coming from humans for the pathology case, and the dermatology case, it came from alternative sort of sources. And again, what you see is at least it performs as well as the human. So interestingly, 3 cases, very recent. And what is the you know, what do these problems have in common? Well, the first thing which they have in common, which is very interesting, is they actually use the same neural net. So these neural nets this neural net Inception v3 is trained by Google on your images, you know, you upload from your vacation and your family and stuff. And that's the basis for all of these 3 algorithms. Of course, they get fine-tuned, so this is sort of the starting point. And then based on the particular data set, they get fine-tuned to improve on this particular task. Now, that to me is very interesting because it means that there is an enormous amount of transfer that you can do between these different tasks. The other thing which is interesting about these tasks, actually, is that you could have rotated the image, and you would sort of have had another valid image to use. And people, I'm sure they did that. They do data augmentation, so they augment the data in various ways. But this is one way to augment your data set with simply rotating the image and then pushing it as an additional data point through the neural net, an additional data point. So this is one example where sort of this is work with Taco Cohen. So he's been the driving force between this project, a very talented student, actually worked with Jeff as well. So the idea is here, how can we improve these CNNs by exploiting these symmetries better, right? So is the best we can do just rotating the image and then using it as an additional data point, or can we do better? And here the idea is, so think a little bit about what makes convolutional neural nets so effective. Well, the first thing is this idea of weight sharing, where you're not interested in necessarily where something is, but you're trying to find something irrespective of where it is. You're trying to find what is in the image. And so you're basically shifting a particular template and you're searching everywhere in the image. So you can think of that as sort of a translation invariance. It's a symmetry. And you only use very few weights, which are the weights of that one particular template, and not have a set of weights which is equal to the number of pixels of the image. And the other thing which is a bit deeper, I think, is equivariance, which is that if you change something in the image, then the hidden representations of your neural net need to change in predictable ways. And I'll give you a few examples in a minute. And that's sort of an important, I think, principle, this equivariance of these representations relative to symmetry transformations. Right? And if, here's an example. If you wouldn't be doing that, then this would be a perfectly fine sort of image of a human being. It's invariant to, to the location or the relative locations of all of these objects, all of these sort of parts in the image. But of course, this is not really what we would want to have as a sort of representation of the human. So here's a little bit of a demo of what we mean by that. So here we do a convolution of this one. This is the filter, and the filter is dark on this side and light on this side. And what it does is it convolves this image, and it finds the edges of this sort of image. Now the image is moving, but let's think if the image is standing still, and you would have an ordinary convolution. So this is a normal convolution. So it would find these two edges which are sort of vertical, right? Now if we move the object in the image, then the representation, which is this, also nicely sort of shifts with the moving of the object. So that's what we call equivariance. Now if you do this for rotation, so we take exactly the same procedure, but now we rotate the bar around, then you see that the activations of the filtered image are very different. Right? There are, here there are sort of two long white bars, and here there is, two long white bars, and here there's two short white bars. And so if I would want to sort of detect, I want to build a layer on top of this, where I want to sort of find sort of this structure, right? Here I could do it with a convolution. I could take some detector that detects these things and then shift it, and I'll find it wherever it is. But like here, I will find it here, but I won't find it here, because it's a very different activation. So, and this is sort of a much older sort of video where we see equivariance on sort of ImageNet images. This is from Jan de Koen a long time ago, where here you can see if you translate the image, the activations here of all the filters, they're just translated, but if you rotate it, you see things are changing here, which makes it very difficult for the second layer to latch on to structure, because it's all changing if you're rotating. So then Taco found sort of an interesting solution to this problem, which is, he says, well, can we come up with a new convolution that will make sure that the hidden representation that you create after convolving will have a very predictable sort of transformation, not just under translations, but also under rotations, for instance, here, or mirror symmetry. So the idea is that this is a normal convolution, so you take an image and you convolve it with this patch and you sort of get this filter map. Here, you do it 4 times if you want to be equivariant to 4 rotations. So the first one is you sort of filter like this, so you produce this one, and then you rotate it. So here it's rotated, and then you produce this one. So now instead of 1 filter map, we have 4 filter maps. And a little bit of more sort of math, the way you would write it out is that, you can sort of think of a convolution as follows based on translations. You take your F is an image, you evaluate it at a pixel X. Now, one thing you can do is you can translate that image. So you translate, let's say, the F to the right here. You can define that as the evaluation at F at the point X minus F, so shifting in the other direction. That's the definition of the translation of the F. And then the convolution is nothing else as taking a filter, translating it to some point S, taking the inner product with filter K, and then sum over all the x's, sum over all the filter maps, and then you get your convolved image, and then it's evaluated at S. Now, S for translation is again sort of a 2-dimensional map, so it's again an image, right? But if you try to generalize that to a rotation, it's slightly different. So now you say, well, let's take another transformation as rotation. So you take the rotation of the f. Now that just rotates the f sort of in this direction. It's the same as f evaluated at r minus 1 r. And then the convolution looks like you take your transformation, like a rotation now, of your filter, then take the inner product of your filter map, sum over all the x's, and then what you get is your convolved image, but then evaluated at G, which is an element of that group. So in this case, if we have 4 rotations and translations, it's going to be 4 images, right? One in this direction, one in this direction, and one in this direction, one in this direction, right? So there's now the output is now 4 filtered images because the group G is a bit larger. Okay, so in order to sort of visualize that, so here we have, again, sort of an input patch, and we convolve it with this L-shaped thing. And sort of, since we rotate the filter map 4 times, you'll see that it detects edges on the left-hand side, here it detects edges from the top, here it detects edges from the bottom, and here it detects edges from the left. So we've rotated this filter map 4 times and convolved it with the input image. And now what does it mean? What does it mean to be equivariant? You say, well, if I first take my image and I rotate it, and then I convolve it with the function psi, with the filter psi, that must be the same as I first convolve the image with the filter psi, and then I transform it with t. So these two things should sort of commute together. And if you then sort of look at how that looks like in sort of animation, so again, if we now take an image like this and we rotate it around, then if you try to see this guy here, it tracks here, and then it goes here, and then it goes here, and it goes here. Right? So what happens is that the filtered image not only rotates inside, but it also sort of moves around in this map. Right? So now the transformation in this space is very predictable. It rotates and it sort of shifts in these 4 filter maps. So in other words, if you do your transformation, if we have this stack of filter maps here, then inside the filter map rotates, but you also sort of permute or shift in this filter stack. And that's the full transformation you have to do in hidden representation. Now, so Taco looked at these groups, the groups P4, which is 4 rotations and translations, as well as P4M, which also has flips in it. Right? So we have a rotation, we have a translation X, translation Y, and we have a flip operation. And so in order to understand what equivariance means in that case, these Cayley diagrams are extremely useful. So this is from Ola's blog. So basically, you can think of these diagrams as representing your group. And a group is such that if you apply a transformation, it will have to stay within the group. That's sort of the definition of a group. So if you start with an image of an F, and you rotate it, so this is a rotation, you go to here, and if you keep rotating, you basically go along these lines. Right? But then if you flip, you go from here. Or if you flip from here, you go to here. And then if you rotate again, you go along these lines. Right? So if you apply something, you just have to follow basically these lines and you figure out what the answer will be. So then, what does equivariance mean in this more sort of complex group? So here we have, again, sort of 4 rotations. And then from here to here, you have the flip. And it basically means very similar to this rotating block, but now sort of more transformations involved. If you first convolve and then you rotate, you go from here to here. So you take this particular filter map, you rotate the filter map, and you shift around in this filter stack. Right? So this is sort of a filter stack of 8 different filtered images. But again, the procedure is very straightforward. You transform inside the image, and you sort of permute in this filter stack. Now, so you can sort of, the nice thing about this is that it's, first of all, it's more data efficient, because now you only have to learn one single filter for all sort of rotations. So you don't have to train 4 separate sort of filter maps for all the different rotations. You train one, and it gets rotated itself, right? So you share more parameters than you would share in a normal sort of convolutional neural net. And what we see is you can sort of use this as a swap. You can just swap out a normal convolution, and you can swap in the sort of equivariant convolution. And sort of here we have some of the sort of benchmarks where if you use a normal convolution, you get these results. And if you start using bigger groups, so this is with rotations, the error goes down. And if you use rotations and flips, the error goes down again. Okay, so that's sort of the procedure. And, this might give us a slightly different view of what it means to disentangle. So disentangling has been a concept which has been used sort of rather vaguely or intuitively. So people think, okay, factors of the input get disentangled at the sort of deep latent representation. So what would that mean? So one way people think about this in the old ICAs, when the hype was all about ICA, people thought about factors of sort of statistical independence. So we're thinking of independent factors of variation, right? Actually, all of sort of these latent variable models have that as an idea underlying it. So here we can start to think of it slightly different, maybe, which is maybe we can think of it as subspaces which rotate or transform independent of other subspaces, right? So if I take an image and I rotate it, then I can think of my latent representations as comprised of subspaces, and sort of they transform into each other sort of independently. So they don't mix, in other words. And so you can think of an object now as basically a trajectory under all these transformations, right, which lives in a particular subspace, and that's an object. And then if you go from one object to another object, you'll have to do different transformation. You have to change the image. And if you do that, you go from here to here in this space. And so in order to do classification, right, you'll have to sort of put a plane here, a hyperplane here, that basically separates these objects, which are now sort of subspaces from these objects. So it's sort of a slightly different view, I think, of what disentangling means. Also, you could even relate these a little bit as well. Okay, so that's the first part of the talk, which is sort of can we be more data efficient, and sort of can we generalize this idea of convolutions to more sort of group convolutions. And then the second part is a sort of different way to generalize convolutions, is from ordinary regular graphs. You can think of a convolution on an image as a very regular sort of grid, very regular graph, square, to irregular graphs. So, and there is a lot of sort of data that's actually organized like that. So this is work with Thomas Kipp and Rianne van den Berg. Right, so let's look at a few examples. Of course, social networks are a particular graph where the nodes represent people, and sort of whether they are friends or not is sort of the edge between them. The World Wide Web, where the edges are one hyperlink to another. Protein-protein interaction networks, citation graphs, and more interesting perhaps is these knowledge graphs, which is like representations where there's entities, the things that sort of we have in our vocabulary as things, and their relationships between them. So, for instance, you take one here. So this thing is purchased this particular object or something like this. So these graphs are enormous, and there's a whole subfield trying to collect these graphs from the web and from text and stuff like that. And I think these are actually important. We want to sort of think about machines in the end that reason, because they represent all the human knowledge in some sense in this sort of data structure. And so what we want is now we want to generalize this idea of convolutions to these irregular graphs, right? And so if we sort of remind ourselves again what a normal convolution is. So let's say you have like a stack of input images or a stack of input, let's say input images. Then you can think of a convolution as sort of moving or propagating information from these neighbors in this graph. Let's say this is a square grid. This is a vector living on a pixel, which is sort of the RGB, for instance, of an image. And you sort of multiply each one of these sort of vectors at these pixels with its own separate weight matrix W, like this. So you multiply W times H for each one of the neighbors, and then you add up all of these linearly transformed neighbors, and then push it through a nonlinearity sigma, and then you have your representation at the next layer, and you keep repeating basically this process. Now the problem is that if you would try to do that on an irregular graph, you run into a problem. So here is again sort of the representation, so the first thing is you have for every node there is a different number of neighbors, but also there is no natural orientation of these neighbors. Right? So if we look at, if we say, okay, let's have a rule where we go clockwise, and we take, we start with a red sort of a matrix W, let's say W1, and then with the next node we encounter, we take a different W2, and then the blue one a different W3, and maybe if there's another one, I'll take yet another matrix, W4. Now, the problem is that if you look at this part of the graph, if I shift, say, this node from here to here, right, the graph doesn't change at all. I mean, this is exactly the same graph, but if I follow my rule, here, the interaction is a red one, a W2, and here, it is a green interaction, right? So what we conclude from this is we can actually not have different weights for these different neighbors. So we have to have, the natural solution therefore is to come up with a single, here. So the natural solution is that, instead of that, we will have to propagate this information from these neighbors by the same matrix W1. And right after we did this, and of course this is based on a lot of other work which I'm not really properly citing here, but there's graph convolutions has been going back further, of course. Yep.
They were labeled, the connections were labeled, so why can't you use weight matrix that represents the label and then propagate by taking also the multiplying by the matrix of the label?
You mean so if the edge is labeled, then you can do it, but you will have to have an actual label on the edge. Yes, but then and we'll do this actually in a minute. So when we do recommender systems or when we can do knowledge graphs, the edges have labels because they are the relations. And then you can have different matrices for the different relations, for instance. Yeah. Okay, so here, so basically we said, very simple, we take, our representations on the nodes H, we multiply them by the same W, and then we normalize. The normalization is actually very important because we have to have eigenvalues sort of close to 1. Otherwise, this thing doesn't really propagate very deeply. You get sort of diminishing or exploding things. So you want to sort of you normalize properly, but there's good ways to do that. And then you have a self-interaction, which could be a different matrix. Push it through nonlinearity and keep repeating. Right? And it's kind of interesting that once we did this, we actually got criticized in a blog by someone saying, well, this is not powerful enough. But it turns out that on a regular grid, this is not a very powerful thing to do. It turns out that on a non-regular grid, actually, even doing something simple like this already gives you very interesting embeddings, as I'll show you in a minute. So then to compose all of these things in a neural net, so you start with your input, then you process for every node, you collect your information from your neighbors, you add your self-interaction, so this is what you do here, you put it through a nonlinearity and you repeat this process, and at the end now for every node you have an embedding, right? So every sort of the input features that were living on the nodes in the beginning, they will be mapped to an embedding in this latent representation. And so you can do with this simple procedure, you can do a couple of things that quite straightforwardly. One is, for instance, semi-supervised learning. So in semi-supervised learning, we have a few data points, so now every node is a data point, and for only a small subset of those, we do have the ground truth labels. So let's say for these, we have the ground truth labels, and for all the other ones, we don't have ground truth. Right? And so one easy thing to do is to, so this is the usual thing people do, which is very competitive, which if your normal sort of error on the labeled nodes, and then you have some kind of smoothness assumption, which says that the prediction on a node and a node that's close by should be quite similar. Right? But there's an alternative to this, which is to say, well, let's, through our graph convolutional neural net, embed all the inputs into some embedding space, sort of a word-to-vec type sort of method, right? And then in the embedding space, let's do the classification in the embedding space. And that's been quite successful, and there's two examples here. But typically you would actually want the embedding to be delivered for that particular classification task, which means you want to do back propagating through the whole thing. So you want the embedding will have to be learned at the same time as the classifier that's being built on top of the embedding as well. So it's quite straightforward. So you take your loss, which is the true label, times the sort of embedding Z, and you try to minimize that, where Z is this graph convolutional neural net. Here's a very simple example. So that is untrained. So it is kind of interesting. So let's say you will not train your embedding. You just take random weights and push your inputs to a latent representation. What you see is that the structure of the graph is already quite nicely sort of represented in the embedding space. So it sort of already does something, and there's actually algorithms that are very much like this. But if you train it, then of course it's even better, right? So the red dots now know to cluster together. Everybody knows, that they have to sort of cluster together, at least the ones that know that they're the same, and then the other ones will sort of group around it. And then I didn't want to show too many sort of results and bold numbers because I think they're quite boring, but I wanted to at least show this result here where, so we took this simple architecture, 2 layers of this sort of graph convolutional neural net, and we looked at these particular data sets. So here's a knowledge graph with, 266,000 edges, so not necessarily super small. So we tried sort of basically all of these methods which were out there to do the semi-supervised learning task. And then if you look at this, actually, we really beat them quite by a large fraction. And this was, to me, a big surprise because I think this is a simple method. And why would it, but it does really do very well. I should also say this is related to work that Rich did and his students on gated neural networks, which actually is quite similar to this result. Came out about the same time. And here's a t-SNE representation of the hidden layer activations. Okay, so then the next step, which is very interesting for knowledge graphs, is link prediction. So now you want to not necessarily predict sort of a label on a node, but now you want to predict edges, right? And in knowledge graphs, this is exactly what you want to predict. You want to sort of say, did this person purchase this particular item? Is basically asking the question, is there a link, a relationship between these two nodes, which says purchased between this person and this item, right? And you can do this with the same technology. So you take your graph. In this case, the input is not only the features living on the nodes, which we call X, but also the connectivity of the matrix. So which node is connected to which other node. And then we train our embedding, which is just our graph convolutional procedure, and we get the same graph, but now on every node we have our embedding. And the next step is to say, okay, start from your embedding, which is Z, and train a separate function that takes as input Z and produces or predicts these links, right? And this is very similar to an autoencoder. So if people who are familiar with autoencoders, it's very similar. Input is X and A, connectivity and node features, produce embedding, and then from your embedding, produce back again your connections, which node is connected to which other node. And the encoder is simply our graph convolutional neural net, and then the decoder was something truly simple here, which I'm sure can be improved. Just take the inner product between, actually outer product if you write it this way, between the embeddings, push it through some nonlinearity that predicts this into a probability between 0 and 1, and then you get your probability of a connection existing between those two nodes. And then you train this, end to end, right? And then, so here's a sort of a little sort of demo of how you can sort of train a latent representation, which makes some sense. Now, so we tried this, and we can actually get very good numbers now on this problem, but I'll spare you the bold numbers. Let me just go to a nice application, which is a recommender system. So you can think of a recommender system precisely in this framework. Right? So in a recommender system, you have people, users. Each user is characterized by a number of features. And at the other axis, you have items, and these items are also represented by certain features, perhaps. And then there's interaction data, which says, this person interacted with this item and rated it 3. Right? And then you map that precisely to a bipartite graph, where on this side you have the users and their features, and on the other side you have the the item features. And now there's relations of different types. So here there's 5 different relationships. Each relation is how many stars you gave to that particular interaction, right? So how satisfied was the customer with buying that particular item? So then the link prediction problem, to map this to a link prediction problem now, is you start with inputs xu, xi, so these are the features on the node and the relations. You produce your embeddings, both for the users and for the items, right? This is a graph convolution, and then the output is, again, try to predict the ratings, which is the link and the type of link, coming from your embeddings Z. Okay, so again, in this case, the performance wasn't state-of-the-art. The performance was maybe the state-of-the-art a year ago in this field, so we have just a few miles to go to actually improve it. And one way we thought would be interesting to improve it is to think of the recommender problem actually as a bigger problem, not just as this simple graph, but what if, here's, let's say, here are the users. Let's say we attach a social network on this side, right? So this guy is friends with this guy, and this guy is friends with this guy. So that basically means you have a lot of extra information here, which is graph-like. But you could also have people which maybe say, well, this type of product, both are technical products, a television and a computer, so they fall in the same sort of category. So I could connect these two together as well, right? So what we really want is to think of this as this graph as part of a much bigger knowledge graph, and then hopefully that we can sort of incorporate external information, right? And so how would we apply this to a general knowledge graph? So a knowledge graph looks like you have a bunch of items, entities in the graph, and then there's relations here. So for instance, this person is a citizen of the USA. The difference is that there's a huge number of relations in this case. So there's not like 5, but there's like millions of relations here. And this actually breaks the learning algorithm. There's too many relations, you get massive overfitting. And so it's a tiny trick. In fact, it's also written quite tiny, but it's a very small trick. But it's actually, this is what makes this thing work, which is you write, so actually, Jeff, this is now a interaction which is dependent on the relationship, right? But since there are so many of these matrices now, you have too many parameters. What we do is we write this as on a basis. So we have a finite set of possible matrices W, and every weight, for every relationship now is a linear combination of this finite set of basis vectors. Right? So then, how can you run this as a graph convolution? You basically say, now we have many different kinds of relationships, and every one has its own WR, which is written like this. But there's also directionality. So there's, of course, you can have, in a relationship which is going this direction, or a relationship is going in the other direction, and we just think of those as well as different relations. So what happens then is, so in order to process it, you take all the activations H for a particular relation, you multiply it by its own WR, right? Then you get this term. You do this for every relation in every direction. You add them all up, push it through a nonlinearity, and then you keep going, right? And then you have 2 types of tasks which are very similar to the task of classification and link prediction. One is called entity classification, the other one is link prediction. Again, we have good numbers in doing this. In particular, the link prediction task is very competitive in this particular problem for knowledge graphs. And in the knowledge graph literature, this is something that only very recently started to appear as a competitive method. Okay, so that finalizes the second part of the talk, the second generalization. And then finally, I want to talk about something which I also got very excited about recently, and is also very much ongoing work. And there is, I think, a lot of very interesting things that can still be done, which is around sparsifying and compressing neural nets. Now, whichever company I talk to, every company wants to compress these neural nets because they're too highly parameterized. and they want to run them on a cell phone, and basically they use too much power. So they're very, very interested in compressing and sparsifying these neural nets so that they fit on your cell phone, but also they don't use too much energy on that cell phone. And so here's I'm going to discuss two ways. The first one was sort of like, okay, well, we should think of this compressing actually as an instance of a Bayesian learning problem. I was interested in Bayesian deep learning, but I think this is kind of a very interesting application of Bayesian deep learning. And it was already quite known that these deep neural nets were vastly over-parameterized. There's this old work called distillation by these folks, where they took a deep neural net, and then they took a lot of new sort of inputs, and they let the network predict the sort of the labels or the probability of the labels, and they added that to the original data set. And then it turned out that you enhance your data sets much bigger, and then you trained on this enhanced data set, you trained a shallow net with many fewer parameters, and then you could get almost the same type of performance, which is kind of interesting, and already pointed to that these neural nets are vastly over-parameterized. Now so what we thought we just, one way to have success is just dig into the old literature, and especially just try to find an old paper by Jeff Hinton and see if you can revive it. So this is an old paper called Soft Weight Sharing, and we thought, well, that might actually be a really nice tool to try to compress these neural nets. And so here's another paper by Jeff Hinton and Radford Neal on thinking about Bayesian learning as a variational sort of framework. And so what you do is you take the evidence, which is the probability of your data set, and you lower bound it by this variation objective, which is basically you introduce a variational posterior distribution over your parameters, which is in itself some kind of parameter, and you say, well, let's take the likelihood term and average it over these variational posteriors Q, and then there's another term here which is a KL, distance between the posterior and the prior, which kind of tells you how complex, how many parameters do you have, how complex is your model at that point. And you can interpret this all beautifully in coding. There's this bits back argument hidden in here, which is the entropy term. And so there's a very nice argument why this should be very relevant for compressing neural nets. So you can think of this as the error, and this is the complexity loss. So I won't go into too much detail because there's not so much time, but the idea is really very simple, and it's almost literally copying the old algorithm onto this new problem and seeing how it works. So what you do is you take a prior, P of W, over your weights, and you write that as a mixture of Gaussians with a very large peak at 0. So you give it a lot of encouragement to build a very large peak at 0, which means that these weights will become 0. They will get pruned because they're 0. But there's also, let's say, 8 other clusters or 16 other clusters that you can maintain. Right? And then what will happen is when you train this, you just train a mixture model on top of your parameters. It's a little bit like a moving target, right? Normally when you train a mixture model on data, at least the target is fixed. But here, you're training the neural net, which means that these parameters are moving. And on top of this, you train this mixture model that's trying to sort of cluster trying to encourage these weights to cluster, but still be useful for the prediction task. And if you do this, this is indeed what happens. So you see that you find that the weights are clustering around these means, which you also train with a very big cluster around 0. And here's sort of a little animation of how that goes. So here's the original distribution of weight. Here's during training you see that it will find these clusters. The biggest peak is at 0 here, and then at some point it has found enough clusters that you can sort of meaningfully assign every weight to a particular cluster. Right? And so how do you then achieve compression? It's very simple. You say you have 8 or 16 different parameters. So those are real numbers. So you have floating point precision for those 16 numbers. Right? But then for every weight, you have to tell that weight which cluster it belongs to. So which of those 8 weights it is, which you need 3 bits for every or 4 bits for every one of these weights to figure out which cluster they are. Okay, but you can get very significant improvements in compression. But the interesting thing is that you will not actually get a big hit in your error. So it's a bit hard to see, but here there's accuracy on this axis, and on this axis there is a compression rate, which is basically how many, if this goes 100, it basically means you keep 100 weights, the rest you will toss out. There's also a bit of there's enough compression going on, like actual tricks to compress these weights to a better format. And then if you do your optimization of hyperparameters correctly, you start somewhere, so you move in this direction. So you can sort of think of this line here as the possible solutions that you can get, where, here, interestingly, in this regime, you improve the solution. So it's not like so you compress and improve your accuracy. Right? It's kind of surprising if you think about it, but it's like a type of regularization. Right? Here it is like you can get up to 60% compression without any loss of accuracy. And then if you want more compression, you have to tolerate some loss. And here in this other one, you can get compression here up to 100 times with barely any loss of accuracy. So to me, this is actually a very interesting issue, because it means that we kind of need this big space to do this optimization. But then once we have the solution, there's also a path to compress it down 100-fold. Yeah.
When you do the forward pass, do you need threading?
No. The forward pass.
Suppose you want numbers,
You might. Yeah, I think you might. And for this particular solution, you might. But then the one that we have after this, you don't, because there we actually compress the individual weights to be fixed point precision. And then I guess the activation can also be encoded at fixed point precision. So for this one, you might. So this is more like an actual compression for the parameters to stick on your, or to live on your device. So here's a little demo that was made by our Russian collaborators, Dmitry Molchanov and Dmitry Vetrov and I'm missing, and Ashuka. So these guys here, which also worked on variational dropout, which is basically you learn the dropout rate, and it's like it acts like an automatic relevance determination where you can basically have a probability of 1 of dropping out a weight or a neuron, which basically means you remove that one. And here you can sort of show they should have showed the filters over time. The compression ratio up here, so it goes up to very high compression ratios. But if you look at the accuracy, it doesn't actually go down, almost at all. Right? And so it basically means that you really only need kind of these weights. I think this is a good model of my brain. I think this is sort of what happening to my brain. I just keep these bits around. Unfortunately, I'm not sure what happens when one of these bits is hurt, because I think it's probably quite important to have these around. And then here's one for the fully connected layer where things are actually even more extreme. The compression is there even more extreme. Just almost everything goes, right, except for these few really important ones that stay around. With compression rates now actually in the latest result, which is now a full Bayesian method, with very sparse priors, we get up to 1,000 times compression rate, which is like, but this includes the actual compression algorithm, like coding. But 1,000 times compression, I think is incredible, actually. I didn't know, when this field started that was achievable. But here you see a nice visualization that you only need to keep a fraction of these weights around for good performance. Now, what does this tell us about, how these neural networks work? I think that's very interesting to think about. Okay, that brings me to the end. So we look basically at 3 sort of extensions of convolutional neural nets. So I argued about equivariance, and that's very important. And we sort of extended convolutions to larger symmetry groups. This is good for more parameter sharing, and therefore it's very good for data efficiency. And especially in the medical domain, I think this could be very useful, because there's not a lot of data around, and you typically have this, for instance, rotation invariance. So you could train much better networks that way. and you get improved accuracy. Basically, you can swap in or out these convolutions as a new module, and you get better performance. So we also looked at convolutions on graphs. So we have a fast end-to-end learning, and we applied it to semi-supervised learning and recommenders and knowledge graphs. And I hope to collaborate more with Rich on this topic, and Ethan also here. And then finally, I looked at sparsifying and compressing these convolutional neural nets. So I think this is a beautiful application of Bayesian methods because it's sort of like model selection in a way. It acts as an ARD, very similar to an ARD process. And we found surprisingly large compression rates with almost no loss in accuracy. And I think we'll see a lot more interesting results on that particular sort of outcome. Thank you very much.
Thank you very much for speaking with us. I'm just curious, how confident are you in those final numbers where the compression ratio was like 200 and the accuracy didn't go down at all? Are you 100% confident that's correct? Or?
So you ask me, how much do I trust my students? We have seen this result not only in our group, but in multiple groups. So it's not, so for instance, the Russian collaborators get independently exactly the same numbers. And so I think this is real. I can't be 100% sure, but I think this is real.
Thank you.
Yeah. So in fact, so for these two, maybe it's very strong. Convolutional neural nets might be slightly less sort of extreme as the ones that we show for the fully connected ones. But I think we still see incredibly large compression rates. It also depends on the data set, perhaps. Oh, the other thing is, when you talk about a compression algorithm, you start from some algorithm that somebody else trained, and then you start to compress it. So if the other person heavily over-parameterized, your compression numbers start to look better, right? So there is a bit of that as well. So you can also train these from scratch. Not actually compressing an algorithm and somebody else's model, but just training your own model, and then it will be a much smaller model. But I think it also reflects maybe a little bit on the literature, is that to get really the last sort of 5% or 1%, people make bigger and bigger and deeper models, but it's like a huge diminishing return curve. But I think these are also heavily over-parameterized.
Points that you made that can we look back at those points and see what they did?
Yeah. It's very interesting. So yeah, so I get this. I need to repeat the question. So that was what is on that particular slide. So can we actually, when we look at these points that remain, the few weights that remain, can we interpret those? As this particular neuron does this thing. So I think we can, but we didn't do it. But I think it's a very interesting question to basically move that weight or remove that weight and see what the impact would be on the final classification. Or there's a bunch of algorithms now that try to at least sort of highlight in the original image, why a particular decision was being made. And I'm sure by perturbing this weight, you can sort of also try to visualize what this neuron was doing. But it's a good thing, and we didn't do it. It's a good question, but we didn't do it.
If you continue to increase the compression ratio beyond the point where the accuracy is stable, how does the accuracy drop off after that point?
Yeah, so here we have the plot. Right, so in this plot, if we go to the right, accuracy here and compression rate here, it's sort of linear curve here. So in other words, if you tolerate a percent accuracy loss, if you tolerate like 0.5% accuracy loss, you can get to 600 times compression.
And if you go, these are still very small losses in accuracy. So if you compress way beyond that, the point where you're breaking it.
Yeah, good question. It will not always be linear. You mean at some point it will just. We didn't do it. Again, very interesting question. If we push this curve to the right, whether, I'm sure it will sort of flatten off or something like this. At some point, the accuracy will completely break down. But yeah, it's good. We sort of thought we would be interested in methods which are degrading too much in terms of their accuracy, but maybe people are interested in some. Yeah. Yeah, it's good. Yeah, some people like that. Yeah, my children like that too.
Have you tried comparing training a network with a small number of weights to training a network with a large number of weights and then compressing it to the same small number?
So repeat the question. Have you compared trying to starting with training a model from scratch to the same sort of capacity, same number of weights, and then compare that with a model that starts out over-parameterizing and compressing it down? The answer, unfortunately, is no. We haven't really explored that, but I can give a bet. I think the one that is started out big and compressed is going to work a lot better. It's going to give you better results, and it might have something to do with optimization. If you give it a lot of degrees of freedom to move around in, the optimization is probably easier. And then once you have found a good point, you can start compressing it down again. A similar thing actually happens for, if I remember well, for decision trees. If you start making a big decision tree and start pruning back, it actually works better than building a small decision tree with the same capacity.
You showed convolutions with groups that have fourfold symmetry, but how much, what is the rotation that, or the smallest rotation you would go to?
Yeah.
In fact, you could go to any number.
Yeah, so they're really good questions. So this is 4 rotations. We now implement things on hexagonal grids, which is 30 degrees rotations. So we sort of insist on staying on the grid, because if you don't stay on the grid, you have to do interpolation. And if you do, I repeat the question. So did you hear the question though? So the question is how many orientations do you need to have meaningfully or how many can you have when you do these group convolutions? So if you have to interpolate, this is not only sort of time consuming and expensive, but it's also accumulates errors. So that's not really great. But Taco did come up with a great solution, which is steerable CNNs. I didn't talk about this. It's in iClear right now. He's talking about that at iClear right now. And so that might be a paper to read up on. Yeah, we also compare to augmentation. So all of these methods are augmented, so even including our own. So it sort of adds on top of the group convolution as well. So that's true. But that's the right control to run. And we did look at all those things, but it adds on to the augmentation result.
Where people try to learn and affine transformation to the entire image before they send it through the network. But they do it like in a global sense, somewhat akin to attention. I was wondering if you could try to learn what sort of transformation you're interested in doing before you apply your kernel.
Yeah, so there is a bunch of work. So the question is, can you also learn interesting deformations or transformations on your input and then use those as augmenting the data set? So I think this process really is different because these convolutional filters are more, they share more data, they share more parameters, and you have this equivariance thing, so it is different than data augmentation, but there is a number of works where people do sort of, I think they have like small deformations or something like this of the inputs. You could imagine that you take and you sort of start to deform it in ways that are actually probable and use those to augment your data set. But I think this is a little bit orthogonal actually. You can do both things and gain improvement.
So your equivariance when you discuss translations and rotations, you looked at all and trying to figure out what other things, learning which things would be invariant.
Yeah, so that's a good question. So the question is whether we only looked at very limited sets of transformations like rotations and flips, but can you learn what transformations, what groups, or what transformations you want to be invariant to? Yeah, we considered this a lot. The question is that we didn't find it very easy. First of all, in frameworks, you have to choose what's called an irreducible representation, and that's sort of a discrete number. It's like for rotations, you have L and M, which is like 1, 2, 3, 4, and then -1, 0, 1, and so you have to choose these irreducible representations, and so it's very hard to optimize over this discrete set. So we got sort of stuck there, and actually, and making it work for much larger groups is also not trivial. So, for instance, scale changes is also not so trivial because the group is not compact, and so there's all sorts of technicalities that will have to be overcome in order to do these things. Yeah.
Okay, that's it. Thanks.
All right, just a quick administrative thing. The talk in 2 weeks is held at the Mars Institute. This Fields is not available. It's by Alex Graves from DeepMind. So I'm just trying to quickly get a rough idea of numbers. So those people planning to attend, can you put your hands up? Those people definitely knowing they're not going to attend? All right. Okay, cool. That's helpful. And last, just thank you to, there's going to be lunch outside for the people at Waterloo. Communitech's providing you guys lunch, so thank you to you guys for wherever you are, arranging for lunch. And thanks to Scotia, Shopify, and GM, as always, to help pay for this. Thank you.